the Golden Gate National Park's Nurseries. I want to thank you all, for those of you who came last night to the Presidio Nursery. It was really nice to meet you. And I'm delighted that we're going to have a deeper dive into nurseries. We'll kick it off with Logan Bennett, who's a master's student in soil science in the Park Lab at Oregon State University, and he'll be speaking about effective solarization.
Hi everybody. So today I'm going to be talking about my research project, and that's titled Determining the Minimum Treatment Area and Importance for Soil Moisture for Effective Soil Solarization. This is going well. And that's kind of a mouthful. So what does that really mean? So what we're really looking at is how does soil moisture and solarization area affect soil-borne pathogen survival? So let's start with talking about solarization. Many of you are probably familiar with this process, but for those of you who aren't, we're just going to go over it briefly. So solarization is a non-toxic method to treat and kill pathogens and weed seeds. It relies on solar radiation to heat the soil, and we use a solarization film. It's plastic that traps the heat in the soil and then kills certain soil pathogens. Typically we do this pre-planting and it's done on bare soil. So here's sort of a basic picture of what we're looking at. So we have the sun emitting radiation through our transparent plastic film. Some of that will reflect back up, and that gets caught by the film. And then it enters the soil and creates this heating profile that goes down and outwards. So solarization is utilized by nursery managers and restoration experts around the world. And in Oregon and California, it's starting to become a more popular method for treating for soil-borne pathogens and weed seeds. So in the Bay Area, solarization has been used to disinfest restoration areas. Recently, native stock was planted in around 9,000 acres of restoration area. Later, this native stock was found to have Phytophthora tentaculata and other species of Phytophthora in it. To remediate that, solarization plots were installed. Solarization plots were installed in optimal and non-optimal areas. Some of them failed. And the question now is, why did that happen? So let's go to my research objective. So we're looking to determine the minimum effective solarization plot size and moisture content for the eradication of Phytophthora ramorum, tentaculata, and pine. So let's talk about an overview of my research. So we conducted research in the summers of 2017 and 2018. We had 2 research sites, Nurseries in San Rafael, California, and the Botany Plant Pathology Farm in Corvallis, Oregon. We used 3 species, Phytophthora ramorum, tentaculata, and pine. We used 3 plot sizes, so 3 different sizes of solarization plastic. Excuse me, 1/2 meter by 1/2 meter, 1 meter by 1 meter, and 2.2 by 2.2 meters, plus a non-solarized control. The plots were either irrigated or not irrigated. This was done pre-putting down the plastic. And then we examined inoculum survival at 2, 4, 6, and 12 weeks. So this is what a solarization plot looks like. So we're looking at the film here. It's 6 mil plastic film, and a mil is 1/1000 of an inch. It's clear, anti-condensation, and we seal the edges with either gravel or soil. So let's examine our research sites. This is our first research site. This is the National Ornamental Research Site at Dominican University, or NORSTEC. Pictured up here is our plot design. So we have a randomized block design for our plots with a irrigation barrier in the middle. The reason we have this irrigation barrier is because we use soaker hoses at NORSTEC. And so we installed that barrier to avoid getting any moisture from our irrigated plots into our non-irrigated plots. At this site, we used Phytophthora ramorum, Phytophthora tentaculata, and Phytophthora pine. We can do that here because this is a quarantine site, so we're allowed to use these species in our research. And this is just a picture of the research plots. This is our second site. This is the Botany Plant Pathology Farm in Corvallis, Oregon. We didn't have the same size constraints that we did at NORSTEC, so we were able to arrange our plots or our treatments in straight rows. They're still randomized block design, but they're in rows instead of that kind of square design. We were able to put a row in between our irrigated and non-irrigated sites, so we didn't need to actually install an irrigation barrier. And at this site, it's not a quarantine, so we were only able to use Phytophthora pine. Phytophthora pine has a higher thermotolerance, or can withstand more heat before it dies, than Phytophthora ramorum. So that's what we use as our surrogate species in Corvallis. So once we had our sites established, we had to establish what we were going to use as inoculum. So for Phytophthora pini and Phytophthora remorum, inoculum is already fairly well established. You can use rhododendron leaves that have been damaged and then infested with either remorum or pini. And you can take a paper hole punch, as pictured here, and make really nice uniform inoculum. For Phytophthora tentaculata, it was a little bit more of a challenge. Rhododendron leaves didn't work as well. So in 2017, we investigated several different types of plant material and paper discs. We ended up choosing oregano stems as our inoculum. In 2018, we looked at several different seeds, including barley, rye, millet, and hemp. We ended up going with rye seeds for 2018 as our inoculum. So once we had our inoculum chosen, we had to actually put it in plots. So pictured up here is our column design. So these columns were what we put our inoculum in to extract during our examination dates. On this side, let's see if I get this button right. Perfect. On this side, we put our inoculum in sachets. So each one of these sachets is holding a different species. So this pink sachet has remorum, this green sachet has pini, and this sachet has the tentaculata rye seeds. So what we did was take these columns and bury one sachet of each species at 5 centimeters, 15 centimeters, and 30 centimeters. So we had 3 sachets at each depth. We used sieve soil, and then we packed it back to the original bulk density of the plot. So once we had these columns made, we put them in the center of the plot. So as you can see, there's 4 columns here, 1 for each extraction period at 2, 4, 6, and 12 weeks. Then we also have our temperature sensors right here. We're going to talk about that in a little while. So we packed our columns, put them in the center of the plot along with our temperature sensors. Then we put our plastic on, and then we surrounded that with either gravel or soil. I mentioned our temperature probes. I thought I'd talk about that a little bit. So we used thermochron eye buttons. They were buried at 5, 15, and 30 centimeters, corresponding to the buried depths of inoculum. And then we had temperature sensors in the center of the plot, in between our columns, and then reaching outwards at 20, 40, and 80 centimeters from the center of the plot, depending on plot size. Here's a side view of that, so it makes a little more sense. So we have our 4 columns. We've removed one for the sake of seeing our temperature plots here. So we have our columns, then we have our first set of temperature sensors, and then reaching outwards to 20, 40, and 80. So this is a 2.2 meter plot. It's our largest size. So we have all of our sensors in this kind of plot. So once the plots were established and we began solarizing, we had to start pulling out inoculum at our survival examination dates. So what we're looking at here is one time period, and what we did was pull 1 column from each plot and then sent it up to Oregon State University for examination. So each one of these plates represents 1 species, 1 depth, 1 moisture treatment, and 1 time period. So as you might imagine, there was quite a bit of plates per sampling period. So this is what 1 plate looks like. This is for Phytophthora remorum. We have surviving discs, 3 out of 10 here. So we have survival at this time period, depth for this species, and moisture treatment, and plot size. That brings us to results. So during 2017 and 2018, we were unable to recover Phytophthora tentaculata from the soil. Pictured here, we have oospores infested in oregano stem tissue. And over here, we have hyphal growth out of rye seeds. So although we were able to create a viable inoculum in the lab, once it was placed in the soil, we were not able to recover it. In 2017, we used PARF as a selective media to try to recover it from the soil. In 2018, we used a less selective media, PAR. We also tried parabating, and we could not recover it from the soil. So let's move on to some other data that we got as results. So what we're looking at here is soil moisture, plot size, and survival at botany plant pathology farm. So this is BPP, the Corvallis site, and this is specifically Phytophthora pini in 2018. So let me help you get familiarized with this. These bars represent plot size. So blue is our non-solarized control, orange is a ½ meter, gray is a meter, and yellow is our 2.2 meters. So these are all depths. Each bar represents our 5, 15, and 30 centimeters. And then over here, we're looking at positive discs out of 10 or % survival. Then we're looking at our weeks. So looking at this graph, we can see that at 2 weeks, we had survival in our largest plot size for irrigated for Phytophthora pini. and no survival over here in the non-irrigated side. But at 4 weeks, we had successfully eradicated Phytophthora pini with our largest plot size in both irrigated and non-irrigated. So regardless of irrigation, in this case, our largest plot size was most effective at eradicating the species. You might also notice that for 2, 4, 6, 12 weeks in both non-irrigated and irrigated, we have survival at all other plot sizes. So now let's examine Norsduck. So we're looking at Norsduck 2018, and we're looking at Phytophthora pini again. So we see a little bit of survival in our non-irrigated at 2 weeks in our largest plot size. But after that, at 4 weeks, in both irrigated and non-irrigated, we've successfully eradicated Phytophthora pini from both with the largest plot size. Now let's look at Phytophthora ramorum. So for Phytophthora ramorum, once again, we see a little bit of survival here in the non-irrigated at 2 weeks, but after that, we've successfully eradicated the species with the largest plot size. At 12 weeks, with ramorum specifically, we see that a 1 meter plot did eradicate the species, but it took 8 more weeks than our largest plot size did. So we kind of want to know what's going on here, so we decided to look at the temperature within these plot sizes. What we're looking at here is plot size and then temperatures reaching outwards. So these are our depths. So the green represents 30 centimeters depth, the red represents 15, and the blue represents 5. And then down here we can see that we're reaching out from 0 to 80 centimeters. We only go to 80 on the largest plot size. And then we're representing this in hours over 35 degrees Celsius. So that's sort of a threshold that we're looking at. So in our non-solarized plots and in our smaller half meter by half meter plot, we see that 5 centimeters gets some hours over 35 at 5 centimeters, but at 15 and 30 there's not a lot of temperature threshold retention there. We really start to see more in our 1 meter plots, but we're not seeing anything at 30 centimeters depth. We really start to see this large temperature increase or retention at 2.2 meters, where we're starting to see almost 600 hours at 35 degrees Celsius in this larger plot size. This can be represented a different way. So this is a heat map from the same time period. These are both from Norsduck 2017. And what we're looking at here is soil heating. It's a soil heating profile of non-solarized down to our largest plot size, which is 2.2 meters. And as expected, in our non-solarized plots, we're not seeing as much heating compared to what we're seeing in our 2.2 meter plots. Just for reference, each one of these has their own depth profile, so this is 5 down to 35 centimeters. And as we can see over here, the closer we are to red, the hotter it gets. And we're reaching out from 0 to 80 centimeters. So our 2.2 meter plots are getting a lot hotter than our non-solarized or even our 1 meter plots. So that kind of brings us back to temperature. At BPP in 2018, we saw the trend that there was more survival in Phytophthora pini than for Phytophthora pini irrigated than non-irrigated soil, and that reflects in our soil temperatures here. So we had a lot hotter soil in our non-irrigated than our irrigated soils. At Norsduck, it got a little more complicated. So we know the trends for survival. At both sites for pini, we had more survival in irrigated soil. For ramorum, there wasn't much of a difference in survival for irrigated versus non-irrigated soil. But we're still working on recommendations for soil moisture, and our irrigation had different results for soil temperature between the two sites in 2018. That can be chalked up to the many differences in sites, or many differences between the sites that could cause a difference in soil temperature. So we're not ready to make a recommendation specifically on soil moisture yet. We did perform a stepwise regression analysis on the survival of Phytophthora ramorum and pini, and then Phytophthora pini on its own. And what we found in both cases was that plot size had the biggest impact on survival of Phytophthora ramorum and Phytophthora pini on its own, followed by soil moisture, and then depth, and then weed. So let's go to our takeaways. So the important things to take note of here are larger plot sizes are more effective for solarization. Solarization is more effective at shallow depths than deeper depths. The longer time period for solarization, the more effective it will be. More analysis, the the effective moisture is needed to determine the optimum moisture for solarization. The minimum effective plot size at 4 weeks is 2.2 by 2.2 meter exposed film, regardless of soil moisture, and a controlled study of the thermotolerance and phytotics and Taki on this plant. I'd like to take this time to acknowledge our partners at NORSDEC, and then my crew at Oregon State University, and to thank the Farm Bill for funding us. Thank you.